Tonight, we follow the story of what lies beyond the universe. Welcome to the Orbit for Sleep channel. Let us follow the orbit of science and drift gently towards sleep. The question of whether the universe has a physical border begins with how we understand space itself. In daily life, everything has an edge. A table ends. A road ends. Even the ocean, vast and overwhelming, eventually meets land. It is natural to expect the universe to have something similar. But the universe, when examined carefully, follows rules that do not match anything familiar. Modern cosmology shows that space does not end in a literal wall or boundary. There is no surface, no invisible fence, no cliff where space simply stops. Instead, space expands smoothly in every direction. The expansion is not like objects moving through empty space. It is space itself stretching. Galaxies drift apart not because they push against anything, but because the fabric of space grows between them. You can imagine a soft, dark sheet being stretched in slow motion. Every point on the sheet moves farther from every other point, but no new edge forms. There is no corner or border. The stretching is gentle, constant, almost silent. The universe behaves in a similar way, expanding without creating an outer boundary. Even though space does not end, the observable universe does have a limit. This limit is not a physical border. It is the distance beyond which light has not yet reached us. Because light travels at a finite speed, and the universe has existed for about 13.8 billion years, we can only see the light that has had enough time to arrive. Anything farther away remains unseen, not because it is blocked, but because its light is still on the way. This can feel like standing on a quiet beach at night. You look out across the water, but darkness swallows the horizon. You know the sea continues. You simply cannot see beyond the distance your eyes allow. The cosmos behaves in the same way. Our cosmic horizon marks what we can see, not what exists. There is another layer to this horizon. Because the universe expands, distant regions recede from us faster than light can travel. When a galaxy is pulled away by the stretching of space itself, faster than light moves, its light will never reach us, even in infinite time. This creates a limit to what will ever be observable, a boundary of knowledge, not a boundary of existence. Scientists call this the cosmic horizon, and it defines the outer edge of our view. But beyond this horizon, space continues smoothly. Galaxies form. Stars burn. Nothing changes merely because we cannot see it. The horizon is a reflection of our position in space-time and the age of the universe, not a physical property of the universe itself. This leads to a deeper understanding. The universe is boundless, but not fully visible. There is no wall or edge, only a soft limit created by light, distance, and time. Space stretches beyond our reach, much like a dream that fades into quiet darkness as it moves farther away. So, when we ask whether the universe has a physical border, the answer is no. The cosmos offers no edge to touch, no barrier to press against. Instead, it is an ever-expanding field of space, where the limit is not physical, but visual, a horizon shaped by the finite speed of light, the age of the universe, and the quiet, continuous expansion of space itself. When scientists use the word beyond in cosmology, they do not mean it in the same way we use it in everyday language. In ordinary life, beyond describes a location on the other side of something, a mountain beyond a valley, or a city beyond a river. It implies a physical separation, a place you can travel to if you continue moving far enough. But in cosmology, the structure of space-time makes this idea different, softer, and much more abstract. To understand what beyond the universe means, we first need to understand what the universe itself is. In scientific terms, the universe includes everything that exists in space and time. All galaxies, all atoms, all forces, and even the space in which these things exist. If the universe contains space itself, then asking what lies beyond it is similar to asking what lies north of the North Pole. The question seems meaningful at first, but its structure breaks down once we examine the definitions. Cosmologists use the term beyond to explore ideas that exist outside the observable region of the universe, not outside space itself. The observable universe is determined by how far light has traveled since the Big Bang. Because light moves at a finite speed, we can only see a limited portion of everything that exists. This creates a natural horizon around us, shaped by time and the expansion of space. Beyond this observable horizon, there may be endless regions of space filled with galaxies, stars, and cosmic structures. These regions do not exist outside the universe. They exist outside our ability to detect them. We cannot see them because the light from those regions has not reached us yet, or may never reach us due to the accelerated expansion of space. To visualize this, imagine standing in a wide, fog-covered field at dawn. The fog limits how far you can see, but the field itself extends far past your vision. You sense the quiet openness, the smooth continuity, even though the fog hides most of it. In cosmology, beyond refers to everything hidden in that fog, the parts of reality that remain out of view. There is another interpretation used in theoretical physics. Some models suggest that our universe could be just one region of a larger structure, sometimes called the multiverse. In these models, beyond could refer to other bubbles of space-time, each with its own physical laws. This idea is highly speculative and not confirmed by evidence, but it gives a vocabulary for discussing forms of beyond that are not spatial in the everyday sense. Instead, they are separated by differences in physics, expansion, or initial conditions, not by a physical wall. In cosmology, beyond is a conceptual tool. It helps scientists describe limits in our understanding rather than a location at the edge of space. It marks the boundary between what we can observe and what might exist, even though we can never reach it. So, when we talk about what lies beyond the universe, the meaning depends on context. It may refer to regions beyond our observable horizon, to hypothetical structures outside our cosmic bubble, or to a space that exists only in mathematical models. What it never means, in modern science, is a physical place outside the universe, because space itself is part of the definition of the universe. In the end, beyond becomes a word that stretches quietly into uncertainty, like a soft horizon that fades into calm darkness, hinting at more than we can ever see. The idea that space might extend forever invites us to think beyond anything our senses can grasp. Human imagination evolved to understand rooms, oceans, mountains, and distances we can walk or measure. But the concept of infinity is different. It stretches quietly into a realm where numbers become meaningless and where our everyday intuition has nothing to hold on to. Still, cosmology gives us tools to think about it in a clear and grounded way. When scientists ask whether space extends forever, they are really asking whether the geometry of the universe allows it to continue without end. Geometry here does not mean shapes drawn on paper. It refers to how space itself bends or stretches. According to current observations, the universe appears to be flat on large scales. Flatness in cosmology means that parallel lines stay parallel, and triangles have angles that add up to 180 degrees, just like they do in ordinary space. A flat universe suggests that space could extend forever. If you imagine a long, straight road in a desert that never curves or loops back on itself, you get a sense of how scientists think about infinite extension. But even in this flat geometry, infinity is not something we observe directly. It is an extrapolation from what we can measure. To understand why astronomers lean toward the idea of infinite space, consider how matter is distributed. On the largest scales, galaxies seem evenly spread out. No edge or central point has been detected. The cosmic microwave background radiation left over from the early universe also looks uniform in every direction. This uniformity suggests that space does not fold into a closed shape like a sphere. Instead, it behaves more like an endless surface. However, even if space extends forever, our ability to observe it does not. Light takes time to travel, and the universe has only existed for 13.8 billion years. This creates a horizon beyond which we cannot see. The horizon does not imply a boundary. It simply marks the limit of what information has reached us. Imagine walking through a wide, snow-covered field during a gentle snowfall. The white blanket stretches in all directions, but the snowfall and mist hide the farthest parts. You cannot tell whether the field ends miles away or goes on for thousands of miles. The universe presents a similar challenge. It gives us clues, but not certainty. There is a deeper complication. Even if space is infinite, matter within it may not be. The distribution of galaxies might extend for a vast distance, but eventually thin out, or it might continue indefinitely. Observations so far show no sign of thinning, but our horizon limits our conclusions. Another possibility is that the universe is finite but unbounded. This means it could wrap around itself like the surface of a sphere. A sphere has no edge, but it is finite. If you walk in one direction long enough, you eventually return to your starting point. Some cosmological models propose that space could behave in this way, not as a sphere, but as a more complex shape called a three-dimensional manifold. These shapes cannot be visualized easily because they exist in mathematical space, not physical analogies. So when scientists say that space might extend forever, they are not making a definitive claim. They are describing what the current evidence suggests. The structure of space appears flat, uniform, and unbounded. The smoothness of cosmic expansion, the absence of curvature, and the distribution of galaxies all point toward infinite extension. But the final answer remains hidden beyond the limits of light and time. In this uncertainty, space feels like a quiet landscape, illuminated only in patches, with vast regions fading into soft darkness. Whether space is infinite or simply unbounded, its presence stretches beyond our understanding, leaving us with a gentle sense of openness that lies at the edge of cosmic knowledge. To understand whether the universe is curved or flat, we need to examine space on the largest possible scales. In daily life, space feels perfectly flat. When you draw a triangle on paper, its angles add up to 180 degrees. Parallel lines stay parallel. These are features of flat geometry. But the universe contains mass and energy, and according to Einstein's theory of general relativity, mass and energy bend space-time. This bending is what we perceive as gravity. The question becomes, when we zoom out far enough, does this bending curve the universe as a whole? Scientists study this using precise measurements of the cosmic microwave background, the faint radiation left over from the early universe. By analyzing how this ancient light stretches across the sky, astronomers can determine the geometry of space. The results so far indicate that the universe is remarkably flat, with a margin of error so small that any curvature would be extremely subtle. A flat universe means that parallel beams of light remain parallel as they travel. If the universe were positively curved, like the surface of a sphere, light beams that start parallel would eventually converge. If it were negatively curved like a saddle-shaped surface, parallel beams would gradually diverge. Observations show neither convergence nor exaggerated divergence. They show a geometry that behaves almost perfectly flat. To visualize this, imagine walking across a vast frozen lake. The surface looks perfectly level. There is no dip, no rise, no curve that you can detect. Even though the earth beneath the lake is spherical, the part you walk on feels flat because it is so large compared to you. The universe behaves similarly. Its curvature, if it exists, is so subtle that the observable portion feels completely even. But flat does not necessarily mean infinite. The universe could still be finite, yet unbounded. In such a case, space might wrap around itself in a way that is impossible to sense from within. You could travel in a straight line and eventually return to your starting point without ever encountering an edge. This possibility depends on the overall topology of the universe, not just its curvature. Topology refers to the way space is connected, which can be far more complex than simple shapes. Another factor that influences cosmic geometry is the expansion of space. As the universe expands, its shape and curvature become more apparent through how galaxies move and how light stretches during its journey. The faster the expansion, the more the path of light is stretched, revealing clues about the underlying geometry. Current measurements from satellites such as WMAP and Planck show that the expansion fits a flat model extremely well. There is also the role of dark energy, a mysterious force that accelerates the expansion of the universe. Dark energy contributes to the overall shape of space. If dark energy had a different value, the universe might be curved in a noticeable way. But with the values we observe, the balance between matter, energy, and expansion results in flatness. However, this flatness applies only to the observable universe, the region we can access with light. Beyond this horizon, the geometry could change. Space might curve gently in ways we cannot detect. It could bend into higher dimensions or form structures that are invisible to us. The universe could be flat locally, but curved globally, much like a sheet of paper rolled into a cylinder. Each point is flat, but the whole structure curves. So when scientists say the universe is flat, they are describing the portion we can observe based on the best available evidence. The flatness tells us that space is uniform, smooth, and behaves consistently on large scales. but it does not close the door on deeper possibilities. Beyond the reach of light, the universe may reveal curves we cannot see, unfolding quietly in the darkness, like a landscape fading into mist just beyond the horizon. When we talk about the edge of space-time, we are describing a limit in understanding rather than a physical location. Space-time is the fabric that combines space and time into a single, unified structure. According to Einstein's theory of general relativity, space-time bends and stretches in response to mass and energy. But does this fabric come to an end somewhere? Does it stop, tear, or form a boundary? The answer is more subtle than a simple yes or no. To visualize space-time, imagine a calm, dark ocean that extends smoothly in every direction. Waves disturb its surface only when energy is present. Space-time behaves similarly. Masses such as stars and galaxies create gentle curves like ripples on the ocean. But there is no visible shoreline, no place where the ocean ends. Instead, the fabric continues, expanding and evolving as the universe grows. The concept of an edge arises when we look at the beginning of the universe. In the early universe, everything was compressed into an incredibly hot and dense state. This is what we call the Big Bang. It is not a physical explosion in space. It is the rapid expansion of space itself. The Big Bang does not mark the edge of space-time in the sense of a border. It marks the earliest moment where space-time becomes definable. As we move forward in time, space-time continues to expand, but the expansion does not create an edge or a boundary. Instead, it stretches the distances between galaxies, making the universe smoother and wider. If the universe is infinite, it expands infinitely. If it is finite, it expands like a balloon, growing in every direction without exposing any surface or wall. There is another perspective, the edge of the observable universe. This edge is defined not by space-time ending, but by how far light has traveled since the Big Bang. Light has a finite speed, and the universe has a finite age. This creates a horizon beyond which we cannot see. If you imagine standing in a vast desert during a sandstorm, your vision fades into the swirling dust. The desert does not end at the place where your view becomes opaque. You simply cannot see farther. The cosmic horizon behaves in the same way. Beyond this horizon, space-time continues. Galaxies, stars, and structures exist in regions we will never observe. Their light will never reach us because the expansion of space pulls them away faster than light can travel. This does not imply a true edge. It is a limit created by the nature of light and the acceleration of cosmic expansion. But the question becomes deeper at singularities regions where the equations of physics break down. Black holes contain such singularities, where matter becomes so compressed that space-time curves infinitely. At these points, the rules of physics, as we know them, stop functioning. The edge of space-time, in this sense, is not a visible border, but a breakdown in our mathematical understanding. It is a limit of theory, not a physical structure. Quantum physics adds another layer. At extremely small scales, space-time may not be smooth at all. It might behave like a foamy, jittering surface filled with tiny fluctuations. If this quantum foam exists, then the concept of an edge becomes even more abstract. The smallest scales of space-time might not have smooth continuity at all, but nothing suggests a physical boundary. So the edge of space-time is not a wall, cliff, or barrier. It is a conceptual horizon shaped by time, light, gravity, and the limits of our knowledge. Space-time does not abruptly stop. It fades into regions we cannot observe, into scales we cannot measure, and into equations we cannot yet solve. The edges are not physical, they are the soft boundaries of human understanding, stretching quietly into the unknown. When scientists talk about the multiverse, they are not describing a fantasy landscape filled with alternate versions of ourselves. Instead, they are exploring a set of ideas that arise naturally from physics and mathematics. These ideas attempt to answer questions that our single, observable universe cannot fully explain. The concept of a multiverse remains theoretical, but understanding it helps us see why cosmologists consider possibilities that stretch far beyond what we can measure. The most common version of the multiverse comes from cosmic inflation. Inflation refers to the rapid expansion of the universe in the first fraction of a second after the Big Bang. During this expansion, space stretched so quickly that small differences in energy could create separate regions that expanded independently. Each region would evolve into its own universe with its own properties. In this view, the multiverse is not a collection of different places inside our universe. It is a collection of separate universes, each disconnected from the others. To visualize this, imagine a field of soap bubbles forming in slow motion. Each bubble expands, smooth and round, separate from the others. The air inside each bubble represents a universe. The bubbles themselves never touch or share information. They grow independently. Inflation theory suggests that our universe could be one bubble among many. We live inside one bubble, while countless others may exist beyond our reach. Another version of the multiverse comes from quantum mechanics. Quantum theory says that particles exist in multiple possible states until they are measured. One interpretation, called the many worlds interpretation, suggests that each possible outcome of a quantum event actually occurs in a separate branch of reality. Each branch forms a new universe. While this idea helps solve certain mathematical problems, it remains speculative and difficult to test. Some cosmologists propose a different kind of multiverse, one based on mathematics itself. If equations allow for many different ways to form a universe, then perhaps every mathematically possible universe exists. In this case, beyond does not refer to physical space, but to the range of solutions within mathematical structures. These universes are not accessible. They are possibilities implied by the logic of physics. However, the multiverse idea is not universally accepted. Critics argue that if these other universes cannot be observed or measured, then the idea falls outside the boundaries of science. A hypothesis must be testable to be scientific, and so far, no direct test for the multiverse exists. This does not mean the idea is wrong. It means it is difficult to confirm within our current understanding. Still, several clues in our universe push scientists to consider these possibilities. The uniformity of the cosmic microwave background, the fine-tuning of physical constants, and the large-scale smoothness of space suggests that inflation may have occurred. If inflation happened, then the existence of other regions, other bubbles, becomes harder to dismiss. The question then becomes whether these bubbles represent parallel realities, or whether they are simply mathematical consequences of how space-time behaves. The answer remains unknown. The multiverse might be real in a physical sense, or it may live only in the equations that describe early cosmic expansion. So when scientists discuss the multiverse, they are not making claims about alternate lives or mirrored versions of humanity. They are exploring the implications of inflation, quantum theory, and mathematical structure. The multiverse remains a possibility, a quiet horizon of ideas that stretches beyond our ability to observe, reminding us that the universe may be far larger, stranger, and more layered than what we can see. Violate any physical law because nothing traveled through space faster than light. Instead, space itself stretched. Inflation offers elegant explanations for many features of the universe, and it also shapes how we think about what exists beyond what we can see. To understand inflation, imagine a tiny region of space, smaller than a grain of dust. In less than a fraction of a second, that region expanded exponentially, becoming large enough to contain everything we can observe today. This expansion smoothed out irregularities and distributed energy evenly, like stretching a small wrinkle on a sheet until it becomes flat. Inflation turned microscopic fluctuations into the seeds that eventually grew into galaxies. One of the key consequences of inflation is that our observable universe represents only a small patch of a much larger structure. The region we can see is limited by the speed of light and the age of the universe. Beyond this patch, space continues, possibly infinitely shaped by the same inflationary expansion. The expansion we observe today is slower than the inflationary burst, but it still continues. Galaxies move away from us, not because they are flying through space, but because the space between us expands. Light traveling from these distant galaxies gets stretched along the way. This stretching causes the light to shift toward longer wavelengths, a process called redshift. The more distant the galaxy, the more extreme the redshift becomes. Eventually, some galaxies move away from us so quickly that their light will never reach us. Even if we wait trillions of years, the expansion of space will pull them away faster than the light they emit can travel. This creates a cosmic boundary, not a physical wall, but a limit on what we can ever observe. To visualize this, imagine watching a small lantern drifting across a calm lake at night. As it moves farther away, its glow fades. At a certain point, the light becomes so faint that your eyes can no longer detect it. The lantern still exists, and it continues to drift, but it passes beyond your perception. Inflation and expansion create a similar effect at cosmic scales. Inflation also explains the uniformity of the cosmic microwave background. This ancient radiation, left over from the early universe, appears almost identical in every direction. Without inflation, distant regions of the universe would not have had enough time to exchange information or energy, yet they look remarkably similar. Inflation stretches a small, uniform region into a vast, smooth cosmos. Solving this puzzle. Another consequence of inflation is the possibility of eternal inflation. In this scenario, inflation never completely stops. Instead, it ends in local regions like ours, allowing them to become universes while other regions continue inflating. These regions might form separate bubbles of space-time, each with its own properties. This idea connects inflation with the concept of the multiverse, though it remains theoretical. Even though inflation is supported by strong mathematical models and observational evidence, many questions remain. We do not know what triggered inflation or what mechanism caused it to stop. We do not know whether it occurred once or continuously. And we cannot observe inflation directly because it happened long before light could travel freely. Inflation shapes our understanding of what lies beyond what we can see. It paints a picture of a universe far larger than the observable region, stretching into uncharted territory. It suggests that space continues quietly past the limits of perception, carrying galaxies, stars, and unknown structures beyond the cosmic horizon. Like a soft wind expanding across a dark landscape, inflation pushed the universe outward, leaving us with a sense of vastness that extends into the unseen depths of space-time. To understand how space itself might have emerged from quantum fluctuations, we must first step into the strange territory of quantum physics. At the smallest scales, far smaller than atoms or particles, reality behaves in unexpected ways. Empty space is never truly empty. Instead, it vibrates with constant activity. Tiny bursts of energy appear and vanish in moments too small to measure. These momentary flashes are called quantum fluctuations. In ordinary life, everything seems solid and predictable. A stone stays still on the ground. A cup of water sits quietly on a table. But on quantum scales, nothing is still. Space itself flickers with possibilities. Particles pop in and out of existence. Energy levels shift rapidly. Even the vacuum is alive with movement. This vibrant instability becomes important when we talk about the origins of space. One major idea in modern cosmology suggests that the universe began as a quantum fluctuation. Before space and time existed in any meaningful form, quantum energy may have fluctuated in a unique way. That fluctuation could have triggered the rapid expansion known as inflation. Inflation took a tiny region filled with chaotic quantum activity and stretched it into a vast, smooth universe. You can imagine this process as a calm breath inflating a delicate soap bubble. The bubble begins as a tiny shimmer, unstable and shifting. Then, with a single breath, it expands into a round, stable form. In the same way, inflation stretched quantum fluctuations into a large-scale structure where the physical laws of our universe could take shape. Quantum fluctuations also explain how matter became distributed across the cosmos. During inflation, the rapid stretching magnified tiny fluctuations. These slight differences in energy density became the seeds of galaxies. Areas with slightly more energy eventually formed clusters of stars, while areas with slightly less formed cosmic voids. The large-scale structure of the universe, the web-like pattern of galaxies, originated from these tiny quantum ripples. This idea might feel abstract because quantum fluctuations are impossible to observe directly. They operate on scales far smaller than anything we can measure. Yet their effects can be seen in the cosmic microwave background. When scientists analyze this ancient radiation, they find slight temperature variations. These variations match the predicted signature of quantum fluctuations stretched across the universe. Quantum physics also suggests that space-time itself may not be smooth. At the smallest scales, space-time might behave like a jittering foam. Instead of a continuous surface, it could be filled with constant fluctuations, like a quiet sea surface rippling under invisible wind. These fluctuations might be responsible for the very fabric of reality, shaping how particles interact and how forces behave. Another layer of the story involves the uncertainty principle. Quantum theory states that the more precisely we measure one property of a particle, the less precisely we can know another. This uncertainty allows fluctuations to exist because energy levels cannot be perfectly stable. They must shift and fluctuate. Stability on quantum scales is impossible. This built-in instability makes the birth of space from quantum activity conceivable. The connection between quantum fluctuations and the origin of space bridges two very different domains: the tiny quantum world and the vast cosmic world. It suggests that the universe began with something unpredictable and chaotic, yet produced a structure that is orderly and comprehensible. This transition from quantum uncertainty to cosmic expansion is one of the most intriguing mysteries in physics. Though we cannot observe the birth of space directly, the mathematical models fit remarkably well with what we see in the sky today. The smoothness of space, the distribution of galaxies, and the patterns in cosmic background radiation all point toward a universe shaped by quantum fluctuations. In the quiet background of reality, these fluctuations continue. They hum silently beneath every particle and every star. Their presence reminds us that the universe emerged from something subtle, unpredictable, and delicately balanced, a gentle whisper at the beginning of time that expanded into the vast space we inhabit today. To understand the observable horizon, we first need to understand how light connects us to the universe. Everything we see, every star, galaxy, nebula, and cluster is revealed to us through light. Light travels at a finite speed, about 299,792 kilometers per second. While this speed is unimaginably fast, it is not infinite. Because of this limit, the distance we can see is also limited. The observable horizon is the boundary of what light has had time to reach us since the beginning of the universe. The universe is approximately 13.8 billion years old. That means light has had 13.8 billion years to travel. But because space itself expands as light moves, the farthest objects we can observe today are actually much farther than 13.8 billion light years. Their light has been stretched by expansion, and the distance to those objects has grown. As a result, the observable universe extends roughly 46 billion light years in every direction. This defining edge is not a physical wall, but a time boundary. Imagine lighting a candle at night in a vast field. If you watch from a distance, the glow fades gradually. At some point, the light becomes too faint to see, but the field does not end. It stretches beyond your view. The horizon of your vision is determined by the brightness of the candle and the sensitivity of your eyes. In a similar way, our cosmic horizon is determined by the speed of light and the age of the universe. The expansion of space creates another layer of limitation. Distant regions of the universe move away from us because space stretches between us and them. The farther away a region is, the faster it recedes. At extreme distances, some regions recede faster than light travels. This does not break any physical law, because nothing is traveling through space faster than light. Space itself is stretching. But it means that the light from those regions will never reach us, no matter how long we wait. They move beyond our cosmic horizon. This horizon changes over time. When the universe was younger, the observable region was much smaller because light had not traveled as far. As time passes, more light reaches us, and we see farther. But at the same time, expansion pulls distant regions farther away. These two effects, light traveling toward us and expansion stretching space, create a shifting, dynamic horizon. The observable horizon, also defines what we can learn about cosmic structure. When we look at distant galaxies, we are looking back in time. A galaxy 10 billion light years away shows us what it looked like 10 billion years ago. The cosmic microwave background, the oldest light we can observe, comes from a time when the universe was only about 380,000 years old. Before that time, light could not travel freely because the universe was too hot and dense. This forms a deeper boundary, the surface of last scattering, a moment when photons first escaped the dense plasma and began their journey through space. In this sense, the horizon represents the earliest visible moment of the universe. Beyond it lies a time when light could not exist as a messenger. We cannot see through that layer, just as we cannot see the sun's core through its bright outer surface. The horizon becomes both a physical limit and a historical one. Even though we cannot see past the observable horizon, space continues beyond it. There is no reason to believe that the universe ends where our view stops. Scientific models suggest that the same structures we observe, galaxies, clusters, and cosmic filaments, extend far beyond the horizon. Those regions are hidden, not absent. This unobservable territory remains one of the great mysteries of cosmology. It reminds us that we see only a small portion of everything that exists. The horizon is not a boundary of space, but a boundary of knowledge, drawn by time, light, and the expansion of the universe. Like a soft edge fading into darkness, it shows us the limits of visibility, while hinting at an unseen cosmic landscape that stretches quietly into the unknown. When we explore the shape of the universe, we are not talking about shapes in the everyday sense, like circles, squares, or cubes. Instead, we are talking about topology, the study of how space is connected. Topology asks questions about continuity and boundaries rather than size or appearance. Understanding this helps us imagine what the universe might look like on the largest possible scale. The universe may be flat, curved, finite, or infinite, and topology explores how all of these possibilities can exist without creating physical edges or walls. For example, a donut-shaped space called a torus is finite but has no boundary. If you travel in one direction long enough, you eventually return to where you started. This closed, looping structure is one way the universe could be finite yet unbounded. To imagine this, picture a two-dimensional creature living on a donut surface. If it walks straight in any direction, it never encounters an edge. Instead, it loops around and arrives back at its starting point without ever realizing it left. From its point of view, space feels endless. Our universe could behave in a similar way in 3 dimensions. Another possibility is that the universe might be shaped like a 3-dimensional sphere. This does not mean it has a surface like a ball. Instead, it means space is curved in a way that does not create edges. If you travel far enough in a straight line, you return to your starting point because space bends gently back on itself. This idea, called positive curvature, suggests a finite universe with no boundary. In contrast, a negatively curved universe is shaped like a saddle. In this model, space expands outward without looping back. Parallel lines diverge, and triangles have angles that add up to less than 180 degrees. A saddle-shaped universe can be infinite, stretching outward without returning to any starting point. Yet it remains perfectly smooth and continuous, with no edges. Then there is the simplest model, an infinite flat grid. In this model, space extends forever in every direction. There are no loops, no boundaries, and no global curvature. Parallel lines stay parallel, and the geometry is consistent everywhere. This model aligns well with measurements of the cosmic microwave background, which suggests the universe behaves nearly flat on large scales. Topology also offers more complex possibilities. Space could be shaped like a three-dimensional manifold, with multiple connections, twists, or identifications. These shapes cannot be visualized easily because they exist beyond our familiar three-dimensional intuition, but mathematics allows them to exist logically. In a manifold, distant regions of space might connect in unexpected ways. Traveling in one direction might bring you to a completely different location than expected. One interesting idea is that space could have repeating patterns. In this model, the universe could contain multiple copies of familiar structures. Galaxies, clusters, or cosmic patterns might repeat at intervals. If space is connected in a looping way, light from distant regions could travel around the universe multiple times, creating ghost images of galaxies. Scientists have searched for repeating patterns in the cosmic microwave background, but so far, none have been found. Even though these topological models differ greatly, they all share one important feature. None of them require a physical boundary. Whether the universe loops around like a donut, curves like a sphere, stretches like a saddle, or extends like an endless grid, it remains continuous. There is no edge to fall off, no border to reach. Topology helps cosmologists explore the deeper structure of space beyond what we can observe. It shows that even if the universe is finite, it can still feel infinite. And even if the universe is infinite, it can still contain complex connections. The universe may hide its shape quietly within its structure, beyond the limits of light and distance, like a vast landscape whose full geometry remains unseen, gently folded into the fabric of space-time. The story of life on Earth is deeply connected to the structure and limits of the universe. At first, this connection may not seem obvious. Life grows on a single planet, orbiting a single star within a single galaxy. The vastness beyond feels distant and irrelevant. Yet the universe's boundaries, both physical and observable, shape how life could arise, survive, and evolve. By understanding these limits, we uncover why existence itself is possible. Life depends on stability. Stars must burn steadily, galaxies must remain gravitationally bound, and cosmic structures must form gradually over billions of years. These conditions can only occur in a universe where expansion, density, and energy are finely balanced. If the universe expanded much faster, matter would spread too thin for stars to form. If it expanded too slowly, gravity would crush everything back together in a cosmic collapse. The delicate balance of expansion creates a universe where life can take root. The limits of the observable universe also influence how we understand life. Because we can only see a fraction of everything that exists, we rely on cosmic background radiation and galaxy distributions to reconstruct the overall structure. These observations tell us that matter is spread evenly on large scales. This uniformity allowed stars and galaxies to form in an orderly manner, providing stable environments for planets. Imagine a calm field of grass stretching beyond sight. You do not need to see the entire field to understand that it is broad, flat, and fertile. In the same way, The observable universe gives us a sample of the cosmic environment that made life possible. Even though we cannot see beyond the horizon, the smoothness we observe close to us implies similar conditions beyond. Life also depends on the universe having limits in temperature and energy. In the early universe, conditions were too extreme for atoms, let alone life. As space expanded, it cooled. This cooling allowed hydrogen to form, then helium, and eventually the heavier elements created inside stars. Without these limits, chemistry, the foundation of life, would not exist. Another important limit is time. Life requires long, stable periods where stars shine gently and planets remain in stable orbits. The age of the universe determines how much time life has to evolve. If the universe were much younger, there would not have been enough time for planets to form or for life to develop complexity. If it were much older, stars like our sun might have burned out long ago. The universe's age falls within a window where life has the opportunity to emerge. The large-scale structure of the universe also influences life through the cosmic web, the network of galaxies and dark matter. Galaxies gather in clusters connected by filaments, leaving vast empty regions between them. These structures formed because of tiny fluctuations in the early universe. If those fluctuations had been larger, galaxies would collapse too quickly. If they had been smaller, galaxies would not form at all. The universe's structure sits within the narrow range that allows life-supporting galaxies to exist. The limits of our solar system reflect cosmic limits as well. The distance between stars is shaped by the distribution of matter. If stars were much closer, gravitational interactions could disrupt planetary orbits, making life impossible. If stars were much farther apart, heavy elements might not spread efficiently, leaving the universe with fewer planets. Our location within the Milky Way, neither too close to the core nor too far into the sparse outskirts, gives us a stable environment. These constraints remind us that life is not a random accident. It is shaped by cosmic conditions that make life-friendly environments possible. The universe's expansion, density, structure, and age work together to create a universe where stars burn, planets form, and life can evolve. Even though we see only a portion of the cosmic landscape, the limits we observe reflect deeper truths. Life exists because the universe occupies a narrow balance point between chaos and collapse. These limits shape every chapter of the story of life, linking our small planet to the vast cosmic structure that surrounds it. Like a single note woven into the quiet harmony of the universe. The expansion of the universe is not just a distant, abstract process. It quietly shapes the conditions that allow life to exist. When space stretches, galaxies drift apart, and the distances between cosmic structures increase. These growing distances help reduce destructive encounters, smoothing out the universe and making it calmer over time. If the universe did not expand, matter would remain crowded and dense. Gravity would pull everything inward, creating violent collisions and chaotic star formation. Stars would ignite too quickly and burn out too fast. Heavy elements, essential for planets and life, would not spread evenly. The universe would be turbulent and unstable, offering no long-term environments where life could grow. Expansion changes this. As space stretches, galaxies separate gently, lowering the chance of catastrophic interactions. Collisions still occur, but over billions of years, slow enough for life to evolve undisturbed. In our own Milky Way, stars orbit in predictable patterns because expansion prevents a universal collapse. This cosmic balance allows calm, long-lived stars like the Sun to exist. Expansion also cools radiation. In the early universe, temperatures were extreme. As space expanded, that energy thinned and softened, making it possible for atoms to form. Without this cooling, chemistry, the foundation of biology, could not exist. Expansion slows the universe down, giving matter time to organize into stars, planets, and eventually living systems. Dark energy and dark matter also play roles in this protection. Dark matter holds galaxies together, while dark energy drives expansion. If either force were much stronger, galaxies would collapse violently or fail to form at all. Instead, the universe sits in a narrow, life-permitting balance. Expansion even protects life from high-energy cosmic events. Supernovae and gamma-ray bursts become less threatening when galaxies are spaced far apart. These distances act like a buffer, reducing the chance that extreme radiation strikes a planet at the wrong moment. To picture this, imagine a peaceful meadow stretching wide and open. If everything were crowded together, trees, rocks, and predators, life would struggle. But with space to breathe, growth becomes possible. The universe behaves the same way. Expansion creates room, softens chaos, and provides time for life to unfold. In this way, cosmic expansion acts as a quiet guardian. It spreads matter gently, cools radiation, slows violent processes, and creates stable environments. Without expansion, the universe would be a place of relentless chaos. With it, life has the space and time it needs to flourish. Life and civilization did not emerge in a crowded or chaotic universe. Instead, they arose in a cosmos where vast distances separate stars and galaxies, creating natural isolation. This cosmic isolation, though immense and sometimes unsettling, is one of the key factors that made long-term stability and eventually civilization possible. To understand why isolation matters, imagine a universe where stars sit extremely close together. Their gravity would constantly disrupt planetary orbits, making stable climates impossible. Life would struggle to evolve or survive long enough to become complex. But in our universe, stars are spaced far apart. The nearest star to the Sun is more than 4 light-years away, a distance so large that even destructive stellar events cannot easily harm us. This isolation gives planets the space they need to follow calm, predictable orbits. Earth moves like a steady clock around the Sun, experiencing seasons and climate patterns that remain consistent over millions of years. Without this stability, life would have no chance to evolve beyond simple bacteria. On larger scales, cosmic isolation also shapes galaxies. Galaxies are separated by huge stretches of space, and while they occasionally collide, these events happen over billions of years. The slow pace of interaction allows stars to form gradually, heavy elements to spread, and planetary systems to emerge. A universe filled with constant collisions would be too violent for civilizations to develop. Isolation also protects developing life from extreme cosmic events. Gamma-ray bursts, supernovae, and intense radiation can sterilize entire regions of space. But because galaxies and stars are spread far apart, these events rarely affect planets like Earth. The universe, despite its size, gives life room to grow, even within a galaxy. isolation plays a role in shaping civilizations. The Milky Way is organized into spiral arms, with stars distributed in a way that reduces damaging gravitational interactions. Our solar system sits in a relatively calm region between arms, a zone sometimes called the galactic habitable region. Here, star density is not too high and not too low, creating a balance that supports long-term stability. Cosmic isolation also influences the development of civilizations in another way: communication. The vast distances between star systems mean that any advanced civilization would face enormous challenges in reaching others. This limits conflict and makes cosmic-scale warfare unlikely. Civilizations evolve independently, shaped by their planetary environments rather than by external threats. This isolation encourages introspective growth. A civilization must rely on its own resources, innovate internally, and develop technologies suited to its unique conditions. In this sense, isolation becomes a quiet force guiding cultural and technological evolution. When we step back and observe the universe as a whole, this isolation is not emptiness, it is structure. It is the spacing that allows order to form. It is the calm that gives life time. The vast, silent distances are not accidental. They are fundamental to the slow, delicate process that allows civilizations to rise, think, and look outward into the night sky. Earth occupies no special physical center in the universe, yet its position reveals how the structure of the cosmos shapes the conditions for life. When we say the universe is unbounded, we mean that it has no physical edges, no walls, and no central point. Every observer, no matter where they are, sees themselves as being at the center of the observable universe. This is not because Earth is special, but because light has only reached us from a finite distance in every direction. Our planet exists inside a stable zone of the Milky Way, a region neither too dense with stars nor too empty. If Earth were located closer to the galactic core, the environment would be far more dangerous. The core is crowded with stars, radiation, and gravitational chaos. Supernova explosions occur more frequently, and the dense star field would disrupt planetary orbits. Life on Earth would face far greater risks. If Earth were located far from the Milky Way's spiral arms, the opposite problem would arise. The density of stars would be too low, reducing the availability of heavy elements like carbon, oxygen, and iron materials, essential for planets and life. Instead, Earth sits in a temperate region of the galaxy, where star density is moderate and radiation levels are relatively low. This location also provides stable cosmic surroundings. The Sun has an almost circular orbit around the galactic center, which minimizes violent gravitational interactions. This steady motion allows Earth's climate and seasons to remain relatively stable over long periods. Without such stability, life would struggle to evolve beyond simple organisms. Earth also benefits from the cosmic expansion that shapes the large-scale universe. Expansion ensures that galaxies do not crowd together. It prevents gravitational collapse on massive scales, creating a calm cosmic environment where star systems like ours can maintain long-term stability. The space around us is quiet, not chaotic. Because the universe has no center, Earth is not privileged by position. Yet the combination of galactic structure, cosmic expansion, and local gravitational balance creates a rare pocket of stability. This balance allows Earth to maintain liquid water, a protective atmosphere, and a climate suitable for biological evolution. The cosmic microwave background, the faint glow left from the early universe, also tells us that Earth lies in a remarkably uniform region of space. There are no huge temperature anomalies or distortions nearby. This uniformity hints at a larger cosmic pattern that supports the existence of galaxies like ours. Earth's position can be compared to a single calm clearing in a vast forest. The forest stretches endlessly in every direction, but not all parts of it are safe. Some areas are filled with storms, some with tangled roots, others with deep shadows. Earth occupies one of the stable clearings, a region calm enough for life to grow, yet dynamic enough to support change. In an unbounded universe, position is not about centrality, it is about conditions. Earth exists at a precise combination of distance, density, radiation level, and gravitational balance that allows life to flourish. Our planet is not the center of the cosmos, but it occupies one of the places where the cosmos' quiet order permits life to bloom. Infinity is a concept that stretches far beyond human intuition. Our brains evolved to navigate physical environments, forests, rivers, mountains, not to grasp limitless scales or endless space. This makes infinity difficult to understand, even when cosmology reveals that the universe may behave in ways that reflect infinite or unbounded structure. In everyday experience, everything has a beginning and an end. Roads stop, books have final pages. The sky meets the horizon. Because we rely on boundaries to orient ourselves, the idea of something that has no limit feels abstract and uncomfortable. When scientists describe space as possibly infinite, the concept clashes with the way human perception interprets the world. The universe does not help our intuition. The observable horizon gives us a finite view, a bubble-shaped region illuminated by light that has reached us over 13.8 billion years. This boundary creates the illusion of a contained universe. We naturally imagine it as the edge of everything, even though space continues beyond our view. Our minds anchor on what we can see, not what we can infer. Our misunderstanding also comes from language. Words like beyond, outside, and edge imply physical locations, but in cosmology, they often describe limits of information, not limits of space. When scientists say we cannot see beyond the observable universe, they are describing a gap in data, not a wall in space. Humans instinctively treat conceptual boundaries as physical ones. Another challenge is scale. The numbers involved in cosmic distances are so large that they overwhelm our ability to visualize. A light year itself is already beyond direct experience, and the universe spans tens of billions of them. Infinity multiplies this scale until it becomes meaningless to human senses. Our minds shrink the concept to something simpler, often incorrectly imagining infinity as very large rather than truly unbounded. Time adds another layer. Humans perceive time as a linear sequence with a clear beginning and end, birth to death, sunrise to sunset. But cosmic time stretches far beyond human lifespans. Stars live for billions of years. The universe may continue expanding indefinitely. This scale distorts our sense of cause and effect, making infinity feel unnatural. Yet, despite these limitations, humans continue to explore infinity through mathematics, cosmology, and abstract reasoning. Even though the concept resists intuition, our curiosity pushes us to understand it. Infinity becomes a bridge between the familiar world and the unseen cosmos, a reminder that our perception is only a small window into a much larger reality. From a cosmic perspective, human confusion is natural. Our minds interpret infinity through finite experience, shaping it into something smaller than it truly is. But recognizing these limitations brings clarity. It helps us approach the universe with humility, acknowledging that what lies beyond our understanding may be vast, quiet, and endlessly expansive. When we look far into the future of the universe, we encounter possibilities shaped by physics, but softened by uncertainty. The fate of everything, stars, galaxies, and even space-time itself, depends on how the cosmos continues to expand, how energy spreads, and how matter behaves over unimaginable timescales. Scientists consider several major scenarios, each describing a universe that follows a different path into the far future. One of the leading possibilities is the heat-death scenario. As the universe expands, galaxies drift farther apart. Stars burn through their fuel and eventually fade. Over trillions of years, fewer stars will be born, and the remaining ones will cool into dense remnants. Energy becomes evenly distributed, leaving no gradients to drive motion or change. In this state, the universe becomes dark, cold, and quiet. Time stretches on, with no activity, no new stars, no new structures, just a thin sea of particles drifting through expanding space. Another possibility is a big rip, though this idea is more speculative. If dark energy grows stronger over time, the expansion of the universe would accelerate to a point where galaxies, stars, planets, and eventually atoms themselves are torn apart. Space would stretch so rapidly that even the smallest structures could not hold together. This future depends on the behavior of dark energy, which we do not yet fully understand. A contrasting scenario is the Big Crunch. In this model, expansion could slow down and reverse. Gravity would pull galaxies back together, compressing the universe into a hot, dense state similar to its beginnings. Stars and galaxies would collide violently. Space-time would collapse inward until everything gathers into a single point. This idea mirrors the conditions of the Big Bang, but runs backward. If this collapse reached completion, it might trigger another expansion, a cosmic cycle of birth, collapse, and rebirth. Some theories blend these ideas into a big bounce, where the universe alternates between periods of expansion and contraction. After collapsing, the universe could rebound into a new phase of expansion with different physical conditions. This cyclical model suggests that the universe has no beginning or end, only transitions. There is also the possibility of eternal expansion without collapse or rip. In this scenario, dark energy remains constant. The universe expands forever, growing colder and emptier. Galaxies drift beyond one another's horizons, disappearing from view. Stars fade, planets freeze, and black holes slowly evaporate through a process called Hawking radiation. Over timescales far beyond human comprehension, even the largest structures dissolve. No matter which scenario unfolds, the common theme is change. The universe evolves slowly, passing through phases of creation and dissolution. Its future is a quiet journey shaped by expansion, gravity, and the delicate balance of energy. While these possibilities may seem distant, they help frame our understanding of cosmic time. They remind us that everything, stars, galaxies, and even the fabric of space-time moves within vast cycles of transformation. The universe's future remains uncertain, but it stretches calmly into deep time, guided by the same laws that shaped its quiet beginning. Human consciousness was shaped by the need to survive on a single planet, not by the need to understand the vastness of the universe. Our thoughts evolved to solve immediate problems: finding food, avoiding danger, building shelter. These tasks relied on a sense of scale limited to what we could touch, see, or imagine within a lifetime. Because of this, infinity and anything close to it lies far outside the natural range of human intuition. Infinity challenges the brain in ways that physical sensations cannot. When we attempt to imagine endless space, our minds often substitute something simpler: a very large number, a very distant horizon, or a boundary pushed just beyond visibility. But these substitutes are not truly infinite. They are finite ideas stretched to their limits. Consciousness reaches for infinity, yet falls short, landing on familiar territory. Even our perception of time resists infinity. Human memory is built from moments that form a sequence. We measure time through sunrises, seasons, and years. But cosmic time flows across billions of years, durations so long they become abstract. Our minds cannot fully hold such scales. When we hear that stars live for billions of years, or that the universe might expand endlessly, we interpret these ideas emotionally rather than precisely. Infinity becomes something symbolic rather than literal. Language complicates the challenge even more. Words like forever, endless, and beyond are metaphors. They point toward concepts that have no physical boundaries, but the words themselves are grounded in finite experience. This creates a tension between what we say and what we mean. When scientists describe the universe as possibly infinite, our minds still imagine a shape, an edge, or a limit. Consciousness instinctively adds boundaries, even where none exist. Our difficulty with infinity also comes from the structure of human reasoning. We rely on categories, contrasts, and comparisons. Big versus small, near versus far, beginning versus end. Infinity breaks these categories. It has no opposite, no scale, no familiar reference. When we try to compare infinity to anything else, the comparison collapses. Consciousness seeks patterns, but infinity refuses to fit into one. Despite these limitations, humans continue to explore the infinite through science and mathematics. Equations allow us to describe space without boundaries. Cosmology lets us model universes that stretch endlessly or curve without limit. Mathematics gives us tools that go far beyond intuition. Through symbols, logic, and abstraction, we reach places our senses cannot. Yet, even with these tools, the emotional experience of infinity remains elusive. No matter how many models we build or how far telescopes reach, infinity still feels mysterious. It invites awe, humility, and a quiet sense of wonder. Consciousness does not fully understand infinity, but it recognizes its presence. On clear nights, when we look at the stars, the sky offers a glimpse of the infinite. We see only a tiny portion of the cosmos, but the vast dark surround the stars hints at something boundless. That hint is enough to stir imagination. In this way, consciousness does not grasp infinity logically, yet it feels its weight, an echo of something larger than thought itself, stretching softly beyond what the mind can hold. When we ask what lies beyond the universe, we imagine something, another space, another realm, another dimension. But one possibility is that there is simply nothing beyond. This idea is easy to say, yet extremely difficult to understand, because nothing in cosmology does not mean emptiness. It means the absence of space, time, energy, and location. It means no direction to travel, no border to cross, and no external viewpoint from which the universe could be observed. To approach this idea, imagine a map with no edges. The map represents all of space-time. Beyond its drawn outline, there is not another land or sea, there is no paper at all. In the same way, if space-time contains everything that exists, then beyond becomes a word without meaning. There is nowhere to go because place itself stops being a valid concept. This is difficult for the human mind because our experience is built on boundaries. We understand the world by moving from one location to another. We expect roads to lead somewhere, horizons to hide further landscapes, and oceans to meet other shores. When told that the universe has no outside, our minds instinctively imagine a bubble floating in a larger void. But in cosmology, the bubble is space-time itself. There is no larger void around it. Nothing beyond the universe also changes how we understand existence. It means the universe is not located within anything else. There is no external container holding it. Space itself is what stretches, curves, and expands. Time itself flows forward. The universe does not sit inside a greater structure. It is the structure. This leads to a subtle interpretation. If there is nothing beyond the universe, then the question, what is outside, becomes similar to asking, what is north of the North Pole? The question collapses because its assumptions do not match the geometry of reality. Another challenge comes from how we imagine emptiness. When people think of nothing, they picture a dark void and empty blackness. But blackness is still something. It is darkness in space. True nothingness has no color, no darkness, no shape, no location. It is not a physical state. It is the absence of all physical states. If nothing exists beyond the universe, it also means the universe cannot expand into anything. Expansion refers to distances increasing between objects inside space, not to space stretching into a pre-existing external area. When cosmologists say the universe expands, they do not mean it grows into a surrounding emptiness. They mean the fabric of space itself stretches internally. This perspective can feel unsettling because it removes the comfort of imagining a larger container. But it also brings clarity. It tells us that the universe is self-contained. Its rules, forces, and structure emerge from within. There is no outer boundary waiting to be discovered. In the stillness of this idea, the universe becomes a complete, continuous field. No edges, no surrounding space, no external time. Only the quiet unfolding of space-time, stretching gently from its earliest moment to its unknown future. And beyond that, not a hidden realm or a secret dimension, only the silence of no beyond at all. When scientists describe the universe as having no edges, they are not speaking metaphorically. They mean that space does not end anywhere. There is no wall, no boundary, and no final surface where space stops. This has profound philosophical implications because it forces us to rethink ideas that feel fundamental: beginnings, endings, direction, and location. In daily life, edges define our world. Walls close off rooms. Shores define oceans. Horizons hide distant landscapes. These boundaries shape how we move and how we understand our environment. But the universe offers no such structure. If space is continuous, then the concept of an edge becomes meaningless. There is no outside to step into. There is only the smooth fabric of space-time extending without interruption. This edge-free reality challenges our sense of scale. Humans instinctively look for limits because limits help us understand where we belong. Without edges, the universe becomes a place where orientation dissolves. We are not near the center or near the edge because neither location exists. We occupy a point in an unbounded structure, surrounded by cosmic distances that stretch beyond imagination. The absence of edges also reshapes our idea of origins. When space has no boundary, the universe does not expand into something larger. It expands within itself. The flow of time pushes space outward, but the expansion reveals no outer region. This challenges the emotional comfort of imagining a larger container or a background setting. The universe is self-contained. It has no external backdrop. Philosophically, this raises a deep question. How do we understand existence without an outside? We often define things by contrast. Light versus dark, inside versus outside, beginning versus end. But in a boundless universe, these contrasts weaken. There is no outside that gives shape to the inside. The universe simply is. This has implications for how we think about ourselves. Without cosmic edges, we cannot measure our place in the universe by position. We are not important because of where we are, only because we are capable of observing and understanding. Meaning comes from perspective, not from cosmic geography. A universe without edges also dissolves the idea of cosmic privilege. There is no center of creation, no favored location. Every observer, anywhere, sees themselves surrounded by an expanding horizon. This symmetry suggests that the universe does not elevate or diminish us by spatial location. It reminds us that significance is internal, not imposed by cosmic structure. Finally, the edge-free universe invites humility. It tells us that the limits we perceive are created not by space, but by light, time, and the structure of perception. Where our senses end, the universe continues quietly. This realization pushes us toward a deeper philosophical truth, that the cosmos is vast, not because we cannot see its boundary, but because it does not have one. In this view, the universe becomes a continuous, seamless landscape, one that expands without edges, stretches without borders, and moves through time without needing an outside. The absence of edges is not emptiness. It is freedom from boundaries, a quiet reminder that reality is larger than the structures our minds are built to imagine. Humans rely on boundaries to make sense of the world. From childhood, we learn by identifying edges where objects end, where paths lead, where horizons separate sky from land. These boundaries give structure to our thoughts and safety to our instincts. Yet the universe itself offers no such edges. And this contrast between human psychology and cosmic reality reveals something deep about how we understand existence. A boundary gives definition. It marks where one thing stops and another begins. Our minds use boundaries to organize information, to predict danger, and to feel oriented. Without boundaries, everything feels overwhelming and undefined. This is why concepts like infinity, endless space, or no outside feel uncomfortable. They do not fit into the patterns our brains evolved to use. The universe, however, does not provide physical borders. Space stretches in all directions without walls or edges. The observable horizon limits what we can see, but that boundary is not real. It is created by the speed of light and the age of the universe. Beyond that horizon, space continues smoothly. This mismatch between our psychological boundaries and the universe's lack of boundaries creates a tension that shapes how we think. When people imagine the cosmos, they often picture it as a sphere floating in darkness. This visualization includes a boundary because the mind instinctively seeks one. But the reality of space-time does not resemble a floating object. There is no outside where the universe sits. That idea comes from the human need to locate things within larger frames. This logical need also influences how we think about time. We divide life into beginnings and endings, marking chapters with clear boundaries. But cosmic time stretches across billions of years in a continuous flow. Stars form, burn, and fade without distinct edges separating past and future. Recognizing this fluidity challenges the human desire for neat divisions. Boundaries also help us cope with uncertainty. When something feels limitless, it becomes difficult to manage emotionally. The idea of a universe without edges inspires awe, but also discomfort. It reminds us of our smallness and exposes the limits of our understanding. Boundaries make the unknown feel approachable. Without them, the unknown feels infinite. Despite this, our need for boundaries is not a flaw. It is a tool, a way for consciousness to anchor itself within an incomprehensibly large reality. Boundaries allow us to process information, create meaning, and navigate life. They help us We build coordinate systems, define horizons, map galaxies, and divide time into eras. These constructs help us understand what the universe does not explicitly provide. Even though these boundaries are mental rather than physical, they offer clarity. Ultimately, the human need for boundaries reflects the scale at which we live. Our universe may be unbounded, but our minds live within limits that keep us grounded. Boundaries shape our inner world, even when the outer world has none. And in that contrast, we find a quiet truth. That meaning is created not by the edges of the cosmos, but by the edges our consciousness draws to make sense of it.